the technical recap. My brief today is ideally to share with the participants the activities of the CGE in support of developing countries in the preparation of their national reports to the UNFCCC. So as an introduction, of course, I'll just give you a background of the CGE, and of course the CGE is a consultative group of experts on national communications from parties not included in Annex 1 to the Convention, of course the so-called non-Annex 1 parties. And the mandate of the CGE was renewed at COP 19 through Decision 19 CP19 for another 5 years, which stretches, of course, from 2014 to 2018. The objective, of course, of the CGE itself is to improve the process of and the preparation of national communications and biannual update reports by parties not included in Annex 1 to the Convention by providing technical advice and support to these parties. To ensure, of course, the successful delivery of this mandate, the CGE has prepared a 5-year work program which focuses on 5 strategic priority areas. Namely, of course, the first, to build the capacity of developing country parties to facilitate the implementation of their measurement, reporting, and verification arrangements under the Convention. And 2, to enhance the sustainability of their national communications and biannual update reporting processes. 3, to enhance the collaboration and cooperation with other global initiatives that, of course, I will allude to later in the presentation, and to enhance the communication, and outreach. And then lastly, of course, to ensure availability of resources and optimal working arrangements for the operation of the CGE. The next slide, of course, shows how the CGE views its work and what the CGE, of course, is doing to ensure that its mandate is delivered. And as a way of supporting parties to participate in the measuring, reporting, and verification framework, the CGE has developed and is already implementing training materials that cut across the different areas, of course, especially cutting across 3 main subcategories. The first one, of course, focuses on the preparation of national communications. Of course, whose core elements include information on a general description of the national circumstances and institutional arrangements, emissions, and of course emissions by sources, and the removals by sinks of greenhouse gases through the national inventory report, steps taken or envisaged by the party to implement the convention, and lastly, of course, any other information that the party views relevant to the achievement of the objective of the convention. And this, of course, is anchored on Decision 17 CP8 of the COP8. And then the second, the second category, of course, of training materials and area of focus is on the preparation of biannual update reports. And these, of course, contain updates of national greenhouse gas inventories, including a national inventory report, information, guidelines for national communication, and of course, this again is anchored, of course, on the relevant COP division. And then, of course, the CGE also involved, of course, in another category which is not common to all parties, on the MRV of RED plus, which is voluntary, and this is based on Decision 14 CP19. The guidelines for national communications were established, of course, at COP18 through Decision 17 CP8, and those for biannual update reports were established as COP17 through Decision 2 CP17. The CGE has prepared training materials, of course, covering all these three in the related areas, and to assist parties in the preparation of the relevant national reports. In the area of capacity building, the CGE, of course, has developed tools and guidance materials that are aimed at improving institutional arrangements and gaining access to financial, technical, and capacity building resources. Of course, the CGE has also organized hands-on capacity building regional workshops, again cutting across the different thematic areas, including vulnerability and adaptation assessments, of course, the mitigation actions and their effects, greenhouse gas inventories, amongst others. And the CGE has also developed, of course, a collaboration with the key global initiatives, which include the UNDP UNEP Global Support Program for National Communications and Biannual Update Reports, and of course the Intergovernmental Panel on Climate Change, especially the latter on areas of on the thematic area of greenhouse gas inventory systems. The CGE also hosts monthly webinars, of course, like the one that we are having today, and these cover issues of vulnerability and adaptation assessments, mitigation actions and their effects, national greenhouse gas inventories, and of course the support, which will, of course, will include the finance, capacity building, and technology development and transfer. The CGE also, of course, undertakes the outreach activities, and this includes, of course, the outreach activities through the social media, among other avenues. And of course, and a good example is our Facebook page, of course, which is shown on the screen. And this way, of course, you can easily follow us as the CGE, of course, and of course, keep abreast, of course, with the activities and, of course, what is being planned ahead. In terms of the resources that the CGE has developed, and of course, that are easily accessible by members, and including, of course, even individuals, and of course, which are also easily downloadable, we have again three categories of resources. And the first set of resources, of course, focuses on national communications, covering the thematic areas that are covered, of course, in the national communications, including vulnerability and adaptation assessment. Two, of course, the national greenhouse gas inventories, and then, of course, the mitigation assessments. And therefore, three sub-thematic areas, of course, under national communications. And these are materials that, once again, are accessible and downloadable from the CGE site that we'll share, of course, with you towards the end of this presentation. And then the second set of resources, of course, focuses on biannual update reports, and this ideally is focused on the preparation of biannual update reports. And just like the materials and the resources related, of course, to national communications, again, these are easily accessible and downloadable from the CGE site. And then lastly, of course, there is the other set of resources that targets, of course, the training of the team of technical experts, which is, of course, involved in the ICA process. Of course, we are all aware, of course, that the team of technical experts, based on the relevant COP decision, of course, should first and foremost be nominated by their national focal points. And of course, they also need to undergo a special course that has been designed by the CGE in collaboration, of course, with the Secretariat, and be certified so that they can participate in the biannual update report technical analysis. Of course, this is based, of course, on the decision of the COP at COP19 in 2013, requesting the CGE to develop and organize appropriate training for nominated technical experts for the technical analysis of the BURs. The next slide, which is now on the screen, ideally demonstrates how one can easily access the resources, of course, on the CGE website. And you can see, of course, at the bottom of the screen, a circled area where you have the CGE training materials covering the three major categories. The first training materials. Then the second, the middle one, of course, is covers training materials for biannual update reports. And then lastly, of course, the training materials, of course, for the team of technical experts. And of course, we will undertake the ICA, the technical review, the technical analysis of biannual update reports. Towards the middle right column, one can easily see, of course, another circle in red. And this ideally highlights the area where one can easily find the link for the training materials that are on the online, the e-learning, that are part of the e-learning courses, because many of these courses, of course, also the CGE, as they developed them further and updated them into an easily accessible e-learning course. So, ladies and gentlemen, I think this slide is ideally just to show that it is possible to access the training materials and other resources developed by the CGE from the CGE site. Lastly, of course, I would want to share with the participants some of the other key resources that the CGE has developed and that are easily accessible again and downloadable from the UNFCCC website. And the first one, of course, is the handbook on MRV for parties. And the link, of course, can be seen on the screen. That's the first bullet. And of course, the cover, of course, how the cover looks like, of course, is also shown to the right side of that row. And then the other set of resources, of course, is for those who are interested, is the link to access all the submitted biannual update reports and the related summary reports. Because of course, after every BUR goes through undergoes the technical review process, then of course when the process is concluded in agreement with the concerned party, a summary report, of course, is finalized by the CGE with the assistance of the Secretariat, and this is accessible, of course, under the second bullet. And also, what is accessible, of course, under that bullet is also the report from the different or from the various facilitated sharing of views sessions that have taken place. Because again, the last phase of the ICA process, of course, is the FSB, where of course the party sits in a panel among other parties, and of course shares the lessons, of course, that they have learned while undergoing the ICA process, and of course they also respond to questions, of course, from other parties and other interested parties. And then lastly, of course, there is a link, of course, that allows one to access all the submitted national communications. And again, this might interest many of the participants because it's very advantageous, of course, to learn from those who are ahead of us in terms of their reporting process. So those who have already submitted several national communications or have submitted their BURs ahead of us, and therefore they have also learned through by going through the ICA process. We can learn a lot from them, of course, by addressing these materials. So with that, ladies and gentlemen, I come to the end of my presentation, and I would want to hand over the screen once again to Baba. Thank you very much.
Great. Thank you very much, Stephen, for that presentation. Joel, I'm just going to make you the presenter now. So you should have access. Oh, and all right, and you're unmuted. Yep.
You can hear me. All right. And can you see the screen? CGE training materials on vulnerability and adaptation assessment.
It hasn't come yet. I think it takes a little bit of time to load. So we'll just wait a bit to go. And while your screen is getting ready, I just want to remind the participants to, start sending in questions that you may have. We can allocate them. All right, great. Okay. Joel, over to you.
All right. Thank you, Baba and Stephen. It's a pleasure to be working, and thanks for all of you for listening in. I have the enviable task of trying to give an overview of climate change scenarios, which is a complex and to some extent controversial topic. I'm going to try to talk for about 30 minutes, but in doing so, I'll only be able to touch on some aspects of this. There is going to be time for questions following my presentation, and also I welcome being contacted outside of this. I'll leave that up to Baba to make my email available, but happy to work with folks offline if they have additional questions. And I'm just going to give some brief, focusing mainly on the climate models, why we create scenarios, how we use models, some of the options you have, because you've probably heard about use of the so-called the GCMs and downscaling, and I'll talk about the pros and cons of each of these. Okay, Stephen was talking about where you can get these materials. This is the web page. This is actually the URL at the top of the screen where you can access the CGE training materials for the preparation of national communication. And specifically what we have here are the materials on how you can prepare your vulnerability and adaptation assessments. And we have this handbook. It was published 2 years ago. I had the pleasure of leading it, as well as writing some of the chapters, and we had a very good team addressing such issues as baseline scenarios, climate scenarios, which I'll talk about, also individual sectors such as agriculture and water and coastal. You can see there's the e-learning courses, which is circled over here. Also, and it tends to be the slide at the bottom of the screen here, is Chapter 4, Climate Scenarios. And if you could see it, you would see something similar to, there's my cursor, to what we see in Chapter 3. There's a handbook, which actually is a written description, a chapter, which I'd encourage you to read, by the way, because it goes into a lot more depth. And then there are the presentations. So there's several presentations on these topics. All right, so I encourage you to go to that webpage. So in this talk, I want to very briefly talk about observed data, where you can get data, because that's important to sort of know what your current climate is and have the data to do further analysis. I'm going to spend most of the talk talking about climate change scenarios. Why do we use them, the kind of characteristics we'd like them to have. And these are important to keep in mind as you go through using them. Never lose sight of why we do these scenarios. And then talk about the use of climate models, the global climate models, GCMs, and also several downscaling techniques. And I'll briefly mention some tools that are out there that can help you access model information or prepare it or even display results. And I'll give you some final thoughts. Okay, so let's begin with baseline climate data. The reason that this is important is because in many cases it's sort of understanding what your current climate is, but also some scenarios actually require that we sort of take the baseline data and then we change it. We might add a certain amount of temperature increase, for example, to simulate climate change. So specification baseline data helps us identify key characteristics of current climate, and I would add in not just averages, average daily temperatures, monthly, average maximum, average minimum, seasonality, wet season, dry season, or if you're in mid or high latitudes, fall, winter, spring, summer, trends and variability, what we're seeing, extreme events, and even local weather phenomena. So there are a number of issues in terms of a baseline data set. One is how long a record should I use? Which period? Well, the World Meteorological Organization recommends using at least 30 years to define a climate. And the reason being a shorter period might be dominated by a drought or a wet period, or maybe an unusually warm or cool period. So 30 years is the minimum to define a climate, recognizing, of course, that in many cases there are gaps in data, and you do the best you can, use what you have. If you have a longer period, that is always better, particularly for extreme climate, and I'll talk a little more about that later. But if you're interested in a 1 in 50 or 1 in 100 year event, well, there are statistical techniques to estimate that from 30 years of data, but you'd rather have more data, 50 or 100 years. And in some cases, many places around the world, there are very long records. So what data sources are available? Here are some with some websites. The IPCC Data Distribution Center is a good place to start. It has access to a lot of the climate model projections. The International Research Institute at Columbia University has a lot of observed data. The Tyndall Center for Climate Research has a gridded global data set. The next two are data sources from the United States that are global: NOAA's Global Historic Climatology Network, and NASA, which also has some data sets. And the final one is the Princeton Terrestrial Hydrology Research Group, which has gridded data that's around the world that's been used in many studies as well. So again, these links should work, but if there are any issues, please let us know. And there may be other data sets too that we haven't included, and we welcome your input on those. All right, let me now turn to this issue of climate change scenarios. So why do we do them? The main reason is, and this is a key thing, it's a fact that the climate is changing. We are very virtually sure that we, humanity, are the cause, and therefore we fully expect the climate to keep changing. So we know it's going to get warmer, we know sea level's going to rise, but we can't say exactly what the changes are going to be. We cannot make a forecast. A forecast is what the weather person tells you today is going to be a high in the 20s with a 38% chance of rain. We can't say that for the year 2050. We know it will be warmer, as I said, and other conditions will change. But what we can come up with are possibilities of change to help us understand what can happen. So scenarios are plausible combinations of variables consistent with what we know about human-induced climate change. So the first part is that they're plausible. In other words, they have to be physically consistent with each other. They can't violate laws of Newtonian physics, in terms of conserving energy and mass. And if it's, for example, if it's cloudiness decreases, we expect more of an increase in temperature. If we get more clouds, then maybe temperatures don't go up as much. Those kind of things. Also consistent with human-induced climate change. The scenario should basically show an increase in temperature, increase in sea level rise. Precipitation's more complex. That's going to vary, but we do expect these to be scenarios of global warming. So typically we use model projections, and I'll talk a little bit about that in a bit, but the models are the only really good information we have on what may happen in the future. Yes, in the past, millions of years ago, greenhouse gases were higher, but things were different. Also, we don't have a good record. Certainly, we don't have daily climate from millions of years ago. So if we want to get the kind of detail at at a monthly or daily time step, as well as at the geographic scale, it's the models that tell us what could happen. But, and I'll repeat this, models are simplifications of reality, so we want to be careful with them. But each scenario will take an individual model output, and there are some, we're going to talk about these GCMs. There are about 40 of these, and each of them will simulate future climate. And they don't all agree with each other, but we can take the output from one model and say, well, that's a possible outcome. We can take the output from another model, say that's another possible outcome, and we have a whole bunch of scenarios. And as I said, these models, they differ substantially. They tend to all show warming, but they might show different levels of warming. Where you'll really see differences in many regions of the world is one model might show it getting wetter in a particular month, another model might show it getting drier. So that's why, okay, well, here's one scenario, warmer and wetter, another scenario, warmer and drier. But we can use these to help understand several things. First, what are possible changes in climate? You know, we say that we look across the range of model projections. There's a range of possible changes in climate. One thing to keep in mind, though, is that what's completely possible, the possibilities also may be outside what the models project. The models don't define all the possibilities, but at least the minimum range of possibilities, so they help us understand that. We can also use them, for example, we can run crop models, or we can estimate water runoff or change in vegetation, and they can help us understand how key systems may change under climate change. So we can understand impacts, sensitivities, key vulnerabilities, and we can finally use these models to help us look at adaptation strategies. We might say, well, let's try a new crop rotation or some new policy. Let's see how it does under this particular scenario. How does that do? Let's look at another scenario, that kind of thing. So that's how these models and how these scenarios are typically being used. Okay, so the characteristics. First, the model, any scenario should be consistent with global projections of climate change. I mentioned earlier, they should show warming. Now, you know, the projections are, you know, we expect anywhere from about 1 or 2 degrees Celsius by the end of the century to as much as maybe 4, 5, or 6 degrees Celsius. That's global average. It's going to vary by region. But, you know, if a scenario is showing a decrease in temperature, that would have to need some explanation, or a very large increase in temperature also may need some explanation. Physically plausible, as I mentioned before, the variables need to be consistent with each other. You know, again, you know, conserving energy, conserving matter, that kind of thing. They need to be applicable for use in vulnerability and adaptation studies. This is important. First, you have to have the variables you need. Typically, you get temperature and precipitation out of the scenarios, and for some applications that's fine, but other applications like crop models, they may need humidity. There's some applications may need wind speed, solar radiation. Those are some of the variables that may be needed. So you have to make sure you have those from the scenarios. This question of resolution is important. First, at a spatial scale, we'll talk about the GCMs in a moment, because those do not have sufficient spatial scale for local analysis, but it has to be at a scale where you're doing analysis. So, for example, if you're looking at a watershed, you need to have projections down to the scale of the watershed, maybe even to individual branches of streams. Farm field, might have to take it down to a farm field if you're looking in agriculture. And then temporal resolution. You know, some models can run with monthly output, but many applications go with daily output, or I should say input of climate data, or even sub-daily. Some people even need hourly or 3-hourly data if you're looking at things like short-term flooding. Number 4 is very important. There should be a plausible range of climate change. Okay, this is a key thing. So I mentioned that, you know, some models may show it wetter, some models may show it drier. Well, I'd say if I look across a number of models and some are going wetter, some are going drier, it may not be clear if a region is going to get wetter or drier. If most of the models, the vast majority, show one change, we might say, well, maybe most of the models are showing this, so we might think it's more likely to be, say, wetter, if, say, 4 out of 5 models show it getting wetter. But even then, we probably should not rule out the possibility of something going the opposite direction. So if you've got some models showing it wetter, some models showing it drier, if you only pick the wet models and use those, you can be misleading people, because they'll say, oh, it's going to get wetter. There's no scenario of it getting drier. And they won't look at the vulnerability of being drier, or they may not look at how adaptations perform if it gets drier. So capture the plausible range, particularly on precipitation, but also on temperature and other key characteristics. And finally, you know, these scenarios need people like you who are listening in need to be able to use them. You need to be able to get the data, get the scenarios, apply them, and be able to interpret the scenario data. All right, let's talk now about climate models. So models are mathematical representations of the climate system. The climate system is very complex. We need these essentially mathematical or computer models because we can't do these calculations in our head. So these models incorporate principles of physics, chemistry, and biology. And we have first one common acronym, these global climate models, GCMs. And by the way, sometimes they're referred to as general circulation models. That's a class of these models, happens to have the same acronym, but we call them now global climate models. They model the whole globe, the entire globe climate. There also are regional climate models, RCMs, that model a portion of the globe, and I'll talk about those in a minute. Okay. So we use the models because they estimate what happens to temperature, precipitation, humidity, wind speed, clouds, ice, all sorts of variables. They'll do it all over the world. I'll talk about the resolution in a minute. And they'll, lots of calculations. One of the things that's important to point out is that as computer speeds have increased, and also as the science has improved, these models are getting a lot better. These GCMs have been around since about the 1950s and 60s, and they have been improving over the decades. Key thing about the models is that we can simulate what could happen as a result of changes in greenhouse gas concentrations. It's very hard to, as I mentioned earlier, to have an analog from the past and say, oh, here's a period where we had similar forcing from models. We get some information from that. These are paleoclimate studies, but we don't get the detail that we can get from the climate models. So we run these climate models with scenarios of typically of high amounts of greenhouse gas emissions, or sometimes they're run with scenarios assuming that we control greenhouse gas emissions. For example, they run with scenarios that are similar to the goal from Paris, stabilizing at 2 degrees above pre-industrial. And again, a key point here, and I apologize for being a little repetitive, but I think it's important, models are really the only way to capture the complexities of what happens to the climate as a result of the increased greenhouse gas concentration. They really are our best tool. They are maligned, but I think they've done well overall. They're not perfect, and that's important to be aware of the limitations. But just because they're not perfect doesn't mean we throw them out. They're good information, and the point is to be good consumers of these kind of things. Sophisticated consumers. Okay, so let's talk about the GCMs. Now, they represent, again, as I said, future climate for all climatological variables, or meteorological variables. They do maintain some degree of internal consistency. That's the pro, and they'll simulate the whole globe. Typically what you do, they'll run these models, and they might start simulation maybe in the middle of the 20th century, maybe even earlier, and they'll ramp up the greenhouse gas emissions, and they'll sort of simulate change in climate over time, going out to 2100, 22, even 2300. They go well into the future. Again, based on scenarios, and these scenarios are generally being provided by the IPCC, the Intergovernmental Panel on Climate Change. This figure in the upper right is important because it shows the resolution of the models. Okay, so first thing I want you to see is, let me see if my cursor is working. Hopefully you can see my cursor. First is you see the model, it simulates different levels of the atmosphere. Okay, so sometimes 10, 20 levels of the atmosphere for each grid box. They also simulate in the ocean, different levels of the ocean. They divide the world into these grid boxes. Okay, so now the size of these grid boxes in the GCMs, I'm sorry, my cursor keeps coming and going, is about 2 to 3 degrees Celsius, about 200 to 300 kilometers across. The problem is, for each grid box, they have to treat it like it's uniform. It's got a uniform topography, it's all land or ocean, there isn't variation. So let's look, if this grid box here, it looks fairly flat, and so that may not be so bad. But then if we look, I'm sorry, my cursor comes and goes. If we look at this grid box here in northern Spain, or let's go a little further north, this one along the coast. So you've got in reality, there's water there, there's coastal area, there's hills. And clearly the temperatures are going to be different, the precipitation is going to be different depending on if it's right on the coast, on the windward side or the leeward side of the hills. The model has to sort of come up with one number. Sorry, All right, that switched there. And so that's a problem. And mentioned earlier, your analysis is going to be a much finer resolution. You may be looking at an individual farm. Apologize for this. I don't know why that keeps moving on its own. That may be located here, and you need to know, gee, that has a particular elevation, and maybe it's down the slope of a mountain or something. That's the problem. So we're going to get into this with the downscaling, but that's the biggest concern about the GCMs. Now, there are roughly 40 of these that are being run for the IPCC, so you get a lot of different projections. Let's see, am I okay, Bob? I think I'm seeing some messages for you. Hopefully people can still hear me. But you get a lot of different projections because each different model will simulate. What they're going to do with each of these grid boxes is they're going to give the change in temperature, change in precipitation, other variables at each grid box for each time step that they model. And they can model at 30 minutes or less. That's what they simulate. They might not save all that data. Often what's saved are monthly projections, and for many models, they are saving daily projections. So now you can get, particularly like the IPCC Data Distribution Center, you can get projections for some GCMs of daily data. That's an awful lot of data. It's going to be a lot to save, but you can get it for each grid box, for each time scale, time step they simulate. Okay, so it's an awful lot of data, but it's still at somewhat low resolution. So because of this low resolution, there is a lot of interest and a lot of use of so-called downscaling techniques. And basically what downscaling is they take the sort of the low spatial resolution of GCMs and they make it higher based on what comes out of the GCMs. So I'm going to talk about three options for doing. One is a very simple option, combining GCM output with observations. Second, statistical downscaling, and I'm also going to talk about something called bias correction is widely used. And then I'm going to talk about so-called dynamic approaches, regional climate models, which essentially are models like the GCMs, but they focus on a particular region, and therefore they can be run at higher resolution. All right. Oops, going the wrong way. All right. Now, important to know, key limitations of these downscaling techniques. They do fundamental reason we model is to get insight into things. It isn't so much to get answers, but to understand systems better. So the downscaling techniques give us more insight about what happens at a smaller scale, a region, or possibly even local scale. But if the GCM gets the basic climate in your region wrong, the downscaling is probably not going to correct that. It's going to give you more spatial precision, but if there's some of the old GCMs were way off. They don't have these problems now. They're not, they might even have high precipitation the wrong time of year. That we don't see now, but the downscaling won't correct that kind of error. The other thing is, I mentioned, is the GCMs give widely different projections of change for a particular region. The downscaling is unlikely to reduce that range of change. If anything, it may increase it. So bear that in mind as you apply these techniques. The other thing about downscaling, it takes a lot of time and effort. Most of these are not easy unless you can use some prepackaged approaches. Okay, the simplest approach is you take an observed database. So let's say you have in your country, you'll have a whole bunch of station data. Okay, and maybe it's even gridded to higher resolution, but you have a whole bunch of data that's observed. Say 1981 to 2010. That's the current 30-year observed data set from data period from World Meteorological Organization. What you can do, the GCM, you can take all the all the stations in a grid point. The GCM will give you a projection for that grid point. So it might say, okay, January 2050 is going to be 1.2 degrees Celsius warmer than, say, our base period, 1981 to 2010. All right. So you could take that 1.2 degrees and add that for January. Add that to the observations for each station in the grid box. Now, one station may be cooler. Maybe in January it's got a temperature of 10 degrees, and so 1.2 plus 10 is 11.2. Another station may be warmer. It shows same day in January it's 15 degrees. So now you're adding the same amount. The 1.2 to 15 in your scenario is now that station is 16.2. So that's a simple approach, and that's done in a lot of studies. One thing to do is to try to be sure that the baseline from the GCM, sort of the simulation of current climate, is consistent with the observed data set. And then you're taking a change from that base. So what you're doing is you're comparing what the GCM, the change simulated by the GCM. One thing, by the way, word of warning, never take the GCM output and use it directly. You should always do some sort of a transformation, like the simple analysis or downscaling. In other words, the GCM will give one number for that entire grid box. That should not be used for all locations in that grid box, okay? So this method can provide daily data at the spatial resolution of the observation stations that you have. One problem is that it assumes a uniform change within a grid box, and if you're using monthly data, over a month. So as I said, every station will have the same change in temperature. Same thing with precipitation. The GCM may show a 10% increase in precipitation for January. Well, the way to apply this is you would take all your observations and any day that in the observed record that you have precipitation, let's say you got 5 millimeters of rain, you would multiply that by, or increase that by 10%. So now I have 5.5 millimeters. And if there's no precipitation, well, 0 times any number is 0, so it still is no precipitation. So you can see what that does is it doesn't change the pattern, the day-to-day or month-to-month pattern of precipitation or temperature, and nor does it change the spatial variability. Everybody warms by the same amount. Precipitation goes up or down by the same percentage. So you don't get variation within the grid box. All right. Now let's move to statistical downscaling. This is a more complex approach. It's a mathematical procedure that basically what you're trying to do is you're trying to find the relationship between certain large spatial scale variables that the GCMs simulate with a much finer scale, typically an individual weather station, so like a point. So for example, we might see, what's the relationship between sea surface temperature or air or pressure patterns or maybe large-scale precipitation with temperature and precipitation at a particular location, typically a weather station. And you establish this direct statistical relationship. By the way, we call these, the predictors are the variables that will the large-scale variables, and the predictands are typically what you're trying to predict, like the temperature and precipitation at those smaller scale. You'll establish a statistical relationship, say, for example, with sea surface temperature and others. And then you'll use that statistical relationship, applying it to the GCM simulation of change in these predictors. So you now say, what does the GCM say about sea surface temperature in the future? Now we're using that relationship between sea surface temperature, say, and precipitation at the weather station to say, how might precipitation change? You'll get what these and tools such as the statistical downscaling method, SDSM, will give you is a projection, an estimate of daily temperature and precipitation at a particular location for a lot of time. They do it GCM by GCM. It's another important thing to point out. These downscaling methods tend to be applied. You apply it to an individual GCM. These things can be done on your own. These tools can be downloaded, and you've got the computer and you've got the data. You may be able to do this on your own. Take some time, though, but they're not expensive to apply. They are time-consuming to apply. One key limitation of statistical downscaling, it assumes that the relationship between the predictors, or what we might call the independent variables, and the predictands, the dependent variables, remains the same. There's no change. So you don't, and these things can change. We don't expect this uniform thing. So be aware of that. Okay, bias correction is another statistical approach. And basically, and now there are many varieties of this happening. Basically, what you're trying to do is there's a bias. The GCM simulates current climate for a grid box where you may be interested in, but typically it's not going to get it exactly right. It may be too warm, it may be too cool, it may be too wet, or too dry. What the bias correction does is essentially through statistical techniques kind of forces the simulation of current climate to look like observations. And it can do this at very high resolution. I've seen some data sets where it goes down to 1/8 of a degree, which is like about 12 kilometers. That's pretty high resolution compared to, a grid, GCM grid box that might be a couple hundred kilometers across. So very high resolution. It can capture climate variance. It's quite useful, particularly useful when in arid and semi-arid areas, because the GCMs, because we use percentage change in precipitation, if the denominator isn't quite right, is too high or low, that throws off the percentage change in a very dry climate. Key limitation is they do not estimate changes in climate, how they vary within the grid box. In other words, they force the GCM output to be consistent with observations, and they use that same forcing for the future projections. But again, one of the things we're interested in is, is the warming uniform within a grid box? Might some areas get more? Might some places within a grid box get drier while other places get wetter? It's a little hard to get at that with a bias correction. But an advantage of bias correction is you can use the outputs directly in your impacts assessment. As I said, don't use the GCM outputs directly, but you can use bias correction. One example of this is the NASA NEXT data set, which is global down to 25 kilometers, so pretty high resolution. There also is another approach called with climate analogs, where people are finding analog high-resolution data sets with analogs that sort of look like what the GCM says future climate is going to look like. So essentially, we're looking for times in the present that have similar characteristics to the projections in the future. They still will be adjusted up, say, to adjust for temperature change. But again, there too, the question is, will that analog hold in the future? Might there be other changes? So again, these techniques like bias correction, statistical downscaling give you a lot more specificity, but understand their limitations. Third approach is essentially the global models the whole world. It captures the energy and the matter and the complexities and the changes. What people have done is have regional models where they might model a continent. It's still driven by a GCM. You got to have something telling it what the global climate is. But then these models are run at much higher resolution, 36 to 50 kilometers. Although that's data. Now they're getting even higher. Some are run as low as 2 or 4 kilometers, which is important, by the way, because you capture cloud processes below 4 kilometers. The trade-off is this: the more resolution you have, the more computing time it takes, and the fewer the years you can simulate. So we like to have spatial resolution, we like to have that, but we also want to simulate many years because climate is variable. And if we simulate, for example, just 1 year, it may be an unusually wet or dry year, it doesn't tell us as much as simulating 20 or 30 years. So RCMs are run at the continental scale with the boundary conditions from the GCM. They do give much higher resolution than the GCM. And so they'll pick up things like lakes, mountain ranges, much better. Remember that when I showed that map of Spain, it had a smooth out, you had that grid box with the water and the mountains. Well, we're running a model at, say, 25, 36, 50 kilometers, more likely to pick up variation, mountains and that kind of thing. Also can some get higher order of climate variability, extreme events and that kind of thing. But again, some limitations. They correct for some, but not all areas of the GCM. A big thing is the parameterization. The RCMs, if they're not down to 4 kilometers, they typically parameterize precipitation, and particularly, say, for thunderstorms, convective events, they're not going to capture them as accurately. So these things are they're doing the best they can statistically, but there can be issues with how well they simulate precipitation. And often, because they may have high spatial resolution, they might only simulate, say, a decade, like the 2040s, which gives you some data, but you'd rather have multiple decades. Some people even do bias correction on the RCM output because the RCM themselves still, when they simulate current climate, still may not get it exactly right. Still may be too warm, too cold, too wet, too dry. So these bias correction techniques that I described earlier are even applied to these RCMs. So this is a lot to think about, okay? Let me just show you a little bit to give you some spatial sense of GCM versus RCM. So this is about a 10-year-old slide. It's a little dated. This is what the GCMs looked like about 10 years ago. Here, the resolution is about 400 kilometers. And so if you're in Central America, you know, and here, if you're in Nicaragua, Western Nicaragua is going to treat as one uniform climate, you know, including El Salvador, including some of the ocean. Eastern Nicaragua is a little different, and it's going to pick up northeastern Honduras. But that's one uniform climate, okay, and it's going to have one uniform change in temperature. This is sort of on the right. It's what an RCM looks like, and it's picking up a lot more detail. Now, this looks good, doesn't it? But you got to be careful, because the real question is, okay, that looks more like reality, with some more warming in some locations, less in others, even a little cooling here, you notice. But one of the things to look at is, what does the RCM simulate? What does the current climate look like? And does that look like real climate? Sometimes you get this detail, but the hot spots are in the wrong location, or the wet spots or dry spots in the wrong location. So that's one test. But, you know, it looks more like reality when you go down these RCMs, and you get much more insight about what happens along the coast, or what happens in a mountain range or valleys, that kind of thing. All right. So before I get into this, let me just pause and just, I'm going to go back. Let me just review. So we have the GCMs, and everything does sort of derive from there. And they're kind of the base of all the information we have, the projections. And you can use their output directly, but again, you should apply it, combine it with observations. Then there are these downscaling techniques. Statistical downscaling you could probably do on your own or have done. It tends to be point by point. RCMs are expensive to run. They require a lot of, you tend to have to see what's available. All of these are run for individual GCMs. These bias correction techniques have been applied to many GCMs, and the data are available. So that's one advantage. It can be like that NASA data set and or others as well. You can just take the data, you can use those outputs directly, but again, be careful about, you know, understanding what they're good and not good at. But in terms of ease of use, those bias correction, if you want high resolution data, maybe some of the easiest things to get. The other thing is, there are these tools that help you. Magic SendGen, developed by Tom Wigley, was developed for an older set of GCMs, not the most recent ones that are used by IPCC, but it's free software. You can get it. You can tell the model, you know, what scenarios you want to assume. Also, if you want to assume that there's going to be a lot of warming or limited amount of warming. And then it uses an approach called pattern scaling to simulate changes at about a 2.5 degree level and monthly temperature and precipitation. SimClim is a tool that can be purchased. I think there are discounts for developing countries. But it uses the same approach in Magic SendGen, but it uses the more recent GCMs. It also addresses extremes. It's a very versatile approach. You can simulate change over individual grid boxes or over a larger area. It even has its own sort of downscaling techniques, although I treat those cautiously. Precis is some regional climate modeling developed by the Brits. I mentioned earlier the statistical downscaling model, SDSM. You can get that on the web. It's developed by Rob Wilby and colleagues in the UK. Again, this is a tool you can downscale. You can apply it yourself, applying to individual GCMs. These last two, Climate Wizard and KNMI, these are sort of visualization tools that you can get on the web, that you can open them up, specify a geographic area, specify a time period in GCM, and they'll show you what changes are being simulated. And they might give you some of the data. It's good for visualization, just for showing people, gee, here's examples of the kind of things that we can see. So another thing, a lot of interest in extreme events. This is harder to do. You know, models tend to be better at averages. They're less good at extremes. You have to be careful about that. One approach is to, first you should use as long a historical, or even if you can get information from paleo records, for some extremes you may be able to. There are ways of making incremental changes in historical extremes consistent, say, with the GCMs. For example, if you're looking at changes in extreme precipitation, you could take projections of temperature and say, well, extreme precipitation will go up 6 to 7% per degree Celsius increase. This is the Clausius-Clapeyron relationship. Assume that increase. So if we have a 50-year historic event, we got 300 millimeters of rain, and now my area is projected to be 2 degrees warmer. Well, that's about a 14 or 15% increase. So, you know, we might add another 45 or even 50 millimeters to that 300 millimeter event. I would consider these sensitivity studies, get some sense of, gee, how might, you know, extreme precipitation change, and you need to apply these, of course, to daily data. And as I said, there are now, there's more GCM data that has simulations of change in daily information, as well as the statistical data sets give that, and the regional climate models give that. Many of the bias correction data sets are monthly changes, by the way, so be aware of that. All right, so this is an awful lot, and I probably succeeded in confusing you. I apologize. It's a lot to absorb. I do encourage you to read the chapter and, you know, ask questions, and feel free to reach out to me. But some key points. Individual scenarios are not predictions of regional climate change. They're an indication. They're a scenario. It's a possibility. We think they're plausible. You should use a wide range of model projections. You can average the models all together, but it would be a mistake to just use that average, because you really should be aware of the range of possibilities. You know, the average might be, you might have wet models and dry models. Maybe on average it's slightly wetter, but boy, you should be aware that it could be a lot wetter or significantly drier. So if used properly, scenarios help us understand and portray, A, what is known about how regional climate may change, although that's kind of the minimum range of possibilities. Remember, change could be even outside what the models say. It certainly can communicate uncertainties. Again, if half the models show it getting wetter, half show it getting drier, well, we're not sure. And you can use them to understand potential consequences. What might happen to crop yields? What might happen to river flow, or that kind of thing? All right, so thank you very much. And Bava, happy to turn it back to you.